Okay, in this video, we're going to talk about section 2.6, dealing with combinations of functions and composite functions. Out of that section, we're going to be finding the domain of a function. Then we're going to combine functions using the algebra of functions by specifying their domains as well. Also, we'll form composite functions and then determine domains for the composite functions and write functions as compositions. All right, first off, we'll talk about the domain of a function. Now, back in chapter 2, in the first section of chapter 2, we did talk about the domain. That's going to be the set of all of your x coordinates or x values. Okay. And pretty much based on what I found in our text, that a function can be represented by, and we're just going to focus on these three: a polynomial, a rational, and a radical function. And the one that we'll focus on is a radical that has an even index. Okay. Now, for a polynomial function, its domain will be the set of all real numbers, or from negative infinity to infinity. Okay. The reason for that is in a polynomial function, any x value that you assign to it, you will always get an f of x value for it. Okay. So polynomial functions are true, will satisfy all real numbers. Now, for a rational function, that's where the variable is in the denominator. Here you have to set the denominator to not equal to 0. That's because you want to find out what values of x that would give you a 0 in the denominator, because as we know, the division by 0 is undefined. And then a radical function, now we're just going to focus on the ones that have an even index here. Here we'll take our expression and set it to be greater than or equal to 0. Okay? Because we can't take the square root or the fourth root of a negative number. That's undefined. Well, not actually undefined. We just can't find a real number where the square root or the fourth root would give you a real number. So here in the first example that I'm going to show you is this. Let's say we want to find the domain of each function. So in part A, we got f of x is equal to x squared plus 3x minus 17. In this case here, we have a polynomial function, okay? Because we're never going to get a 0 in the denominator. It's just a regular polynomial function. Any x value that you assign to it, you will always get an f of x value for it. So for a polynomial function like this one, its domain in interval notation would be from negative infinity to infinity. So it's going to be the entire number line for this, if you were to shade this. Okay, now part B, we got g of x is equal to 5x divided by x squared minus 49. In this case, we got the x in our denominator. This is a rational function. We have a numerator and a denominator, and we got the variable in the denominator. So we're going to take that expression that's in the denominator, which is x squared minus 49. And I'll go ahead and set this equal to 0 because I want to find out what values of x that will give me a 0 in the denominator. All right, in this case here, that x squared minus 49, that's a difference of two perfect squares. I can factor that into two binomials here. So x squared breaks up as x and x. Factors of 49 is 7 and 7, but since it's a difference of two perfect squares, one has to be plus, the other one has to be minus. So we got x plus 7 times x minus 7 equal to 0. And then we set each factor equal to 0. So we set the x plus 7 to be equal to 0. Or x minus 7 equal to 0. And each one of those equations, we're going to solve for x over the x plus 7 equal to 0. If I subtract 7, I'm going to get x equal to negative 7. Or for the x minus 7 equal to 0, if I add 7, that would mean x is equal to positive 7. So at x equal negative 7 or at x equals 7, I will get a 0 in the denominator. All right, so now, and I believe in the homework, they're going to want the domain in interval notation. So if this helps, and it's not necessary that you have to do this, I'm going to put negative 7 here and positive 7 here. So we know at negative 7, we know we're going to get a 0 in the denominator. And at positive 7, we're going to get a 0 in the denominator. Any x value less than negative 7 would work. So that's why I shade to the left. Any x value between negative 7 and 7 would work. So I'm shading in between. And any x value bigger than 7 would also work. That's why I shaded to the right. So my domain, if I go from left to right for this rational function on this number line, that's going to go from negative infinity up to negative 7. Or that's the union symbol, from negative 7 to 7. Or from 7 all the way out to infinity. Okay, so that would be the domain of that rational function in interval notation. All right, the next example is a radical function that has an even index, is the understood too. So that's, we read that as a square root of 9x minus 27. That's equal to h of x. It is a radical function with an even index. So that means we take what's underneath that radical, which is 9x minus 27, set it to be greater than or equal to 0. All right, and we do that because we can't take the square root of a negative number. Okay. So to get 9x by itself, we add 27 on both sides of this inequality. So that means 9x is greater than or equal to positive 27. Then divide both sides by 9. That means x is greater than or equal to 3. Now what that means here is this. Any x value greater than or equal to 3 would work for this function h of x. Any x value less than 3 would give us a negative underneath the radical, and we cannot take the square root of a negative number and try to get a whole number or real number from it. All right, so if you want to do this, you can draw the number line to help you. Well, we know we can include 3. So that's why we have the bracket. Greater than means we shade to the right. Any x value greater than 3 or equal to 3 will satisfy this h of x function. So the domain in interval notation would be this. A bracket at 3 goes on indefinitely to the right. That'd be infinity. So this is the domain for that radical function. Okay, next we'll look at the algebra of functions. That's the sum, the difference, the product, and the quotient of two functions, f of x and g of x. So here we're going to let f and g be two functions here. Now the sum, which is f plus g of x, is going to be the same as f of x plus g of x. So here we're just going to be combining the two functions together through addition. Now the difference, which is f minus g of x, that's just going to be f of x minus g of x. Okay, now with the g of x here, since there's a minus in front, you want to make sure that your g of x function is in parentheses because you're subtracting the entire g of x function from f of x. And then number 3 is the product. Here you multiply the two functions together. F times g of x is the same as f of x times g of x. That's multiplication. And then the quotient, f divided by g of x, will be f of x over g of x, with the provision that g of x is not equal to 0. Okay. Now we're going to use that with these examples here. So in example 3 in your handout, you'll see this. Here we're going to let f of x equal to 3x plus 4 and g of x is equal to x squared plus 4x minus 12. And we want to find the following functions: f plus g of x, f minus g of x, f times g of x, and f divided by g of x. This is at the bottom of your handout here. Not only that, for each one of these, we're going to find the domain of the sum, the difference, the product, and the quotient of the two functions. Let's start with f plus g of x. That's part A. Now, f plus g of x is the same as saying f of x plus g of x. F of x plus g of x. And f of x is 3x minus 4 plus g of x is x squared plus 4x minus 12. And now let's combine like terms here. And I'm going to put these in descending powers here. Like for the x squared, I have nothing to combine with that, so I'll bring the x squared down. And then 3x plus 4x, I can combine that. That'd be plus 7x. And then minus 4 and a minus 12 will be minus 16. Okay, so the sum of f and g of x would be x squared plus 7x minus 16. Okay, now our sum is a polynomial function. That means any x value that you assign to it, you're going to get a value for f plus g of x. So that domain is, since it's a polynomial function, its domain is this. In interval notation, negative infinity out to infinity. So that's your domain for that, for the sum of those two functions. All right, now for f minus g of x, this is part B. F minus g of x means this: f of x minus g of x. Well, f of x is 3x minus 4 minus, now the g of x, since we're subtracting the entire g of x function, we need parentheses. And that g of x is that x squared plus 4x minus 12. Okay, now here that minus sign is going to change the sign of each and every single term in that g of x function. So here I'm going to bring down 3x minus 4. The minus sign makes the x squared minus x squared. The minus sign makes the plus 4x minus 4x. The minus sign makes the minus 12 plus 12. Now we can combine like terms here. Nothing to combine with the x squared, but I do have a minus sign in front, so it'll be negative x squared. Let's see, 3x minus 4x would be a minus 1x, or just minus 8. And then minus 4 plus 12 would be plus 8. So the difference of those two functions, f and g, would be x squared minus 4x minus x, plus 8. Negative x squared minus x plus 8. And again, we have a polynomial function for f minus g of x. So that means our domain is still going to be from negative infinity to infinity. That would be your domain. All right, part C, f times g of x. So here we're going to multiply the two functions here. This means f of x times g of x. So here my f of x is 3x minus 4 times g of x, which was x squared, plus 4x minus 12. All right, the way I'm going to do this, I have a binomial multiplied by a trinomial. That means I need to take the first term of this binomial multiplied by each and every term of the second. So I got to do 3 times x, then 3 times 4x, and 3 times minus 12. So here, 3 times x squared is 3x cubed, because bring down the 3, x times x squared, that's like x to the 1 times x squared, or x cubed. And then 3 times the plus 4x, well, 3 times 4 is plus 12, and x times x is x squared. And then 3x times the minus 12 will be a minus 36x. Okay. And then next I take the minus 4 and multiply by each and every term in the second. So I got minus 4 times x squared, minus 4 times 4x, and then minus 4 times minus 12. Okay, so now minus 4 times x squared will be a minus 4x squared. And then minus 4 times the plus 4x will be a minus 16x. And then minus 4 times the minus 12 plus 48. Now let's combine like terms here. The 3x cubed, I can just bring that down because I have nothing to combine with it. Let's see, 12x squared minus 4x squared. I can combine that to get plus 8x squared. Then minus 36x and a minus 16x. Well, minus 36 and a minus 16, that's going to be a minus 52. Bring down the x, and nothing to combine with the plus 48, bring that down. So the product of f and g of x will end up being 3x cubed plus 8x squared minus 52x plus 48. And again, we ended up with a polynomial function here for the product of f and g of x. That means its domain in interval notation would be negative infinity to infinity. All right, and part D, f over g of x. That's the quotient of f and g of x, which means I have f of x divided by g of x. Well, f of x is at 3x minus 4 over g of x, that's going to be x squared plus 4x minus 12. Now, this would be as far as I can go as far as simplifying this. Okay. Now, we also need to find the domain. This time, the domain is not going to be from negative infinity to infinity because I have a quotient here. Now, I have a rational function. That means I got the variable in the denominator, x squared plus 4x minus 12. I need to find out what values of x that would give me a 0 in this denominator. So I'm going to take that x squared plus 4x minus 12, set that equal to 0, and simplify. Let's see here. It is 3 terms. It's a quadratic, so I can try to factor this into 2 binomials. The x squared, I can break that up as x and x. Let's see, I need factors of negative 12. That's going to give me a plus 4x. Well, let's try 6 and 2. Since the middle term is a plus and the last term is a minus, the larger of these two factors will take the sign of this middle term. So 6 will have to take the plus sign, and the 2 will have to take the minus sign. So here we got 6x minus 2x will give me 4x. So factored, it'll be x plus 6 times x minus 2 equal to 0. And then I set each binomial factor equal to 0. So I have x plus 6 equal to 0 or x minus 2 equal to 0. And then for x plus 6 equal to 0, if I subtract 6, I'll get x equal negative 6. Or for the x minus 2 is equal to 0, that will mean x is equal to 2. So at negative 6 and at negative 2, I will get a 0 in that denominator. Okay. Now, I'm going to draw a number line so that way I can write my domain in interval notation. So I know negative 6 will be here, 2 would be here. And at negative 6 and at 2, I know I'm going to get a 0 in the denominator. So that's why I use parentheses there at negative 6 and at negative 2. Any x value less than negative 6 would work. Any x value in between negative 6 and 2 would work. And any x value bigger than 2 would work. So for the quotient of f and g, its domain in interval notation will be this, from negative infinity up to negative 6. Or from negative 6 up to 2. Or from 2 to infinity. And notice on these, I'm only using the parentheses, no brackets here. Okay. That's how we find the sum, the difference, the product, and the quotient of two functions. All right, here's another example of just that. Let's say we had f of x is equal to x minus 5 and g of x is equal to x squared minus 1. And I want to find each of the following functions. That's the sum, the difference, the product, and the quotient of the two functions. Starting with f plus g of x. That's part A, which is, of course, f of x plus g of x. Now, f of x, of course, is x minus 5, plus g of x is x squared minus 1. And then we combine like terms here. Nothing to combine it with the x squared, so I bring that down. The x, it'll be plus x, but negative 5 minus 1 will end up being negative 6. So I have x squared plus x minus 6 as the sum of f and g. And notice I'm writing them in descending powers, so x squared, then x, and then the constant. And of course, the domain, since it's a polynomial function, would be this, negative infinity to infinity. Okay. I put B, f minus g of x. It was subtracting f and g. So it'd be f of x minus g of x. Now the f of x is, of course, x minus 5, and then minus. Now for the g of x, I'm subtracting the entire g of x function from f of x. So I need parentheses around the x squared minus 1. And then this minus sign is going to change the sign at each and every term inside the parentheses here. So I'm going to bring down x minus 5. The minus sign makes the x squared minus x squared. The minus sign makes the minus 1 plus 1. Now, in this case here, the minus x squared, I'm going to put that first. And then that x, which is plus x, minus 5 plus 1 will be minus 4. And that's as far as I'm going to go with that. So the difference of f and g of x would be negative x squared plus x minus 4. And for the domain, since again it is a polynomial function that I ended up with, that domain would be also negative infinity to infinity. Okay. All right, now part C, f times g of x. Here we're taking the product of the two functions, we're multiplying them. So in this case here, this will be f of x times g of x. F of x times g of x. So f of x was x minus 5 times g of x, that's x squared minus 1. And now we're going to use the FOIL method since we're multiplying two binomials here. And that's this, x times x squared. That's the first times the first. X times x squared, that will be x cubed. And then we multiply the outer, x times minus 1 will be a minus 1x, so just minus x. The inside, minus 5 times x squared, minus 5x squared. Excuse me. And then minus 5 times a minus 1 will be plus 5. Combine like terms here, there's not much you can combine except putting them in descending powers, by the way. This will be x cubed. Then I put the minus 5x squared next, then minus x plus 5. So with this one, there's not much you can combine other than just putting them in descending powers. All right. Now again, this is a polynomial function, so the domain there is, again, negative infinity to infinity. Okay, part D, f divided by g of x. That means f of x is going to be divided by g of x. Well, here f of x, of course, is x minus 5. Divided by g of x, that's x squared minus 1. And that would be as far as I can go with that problem. Now we need to find the domain, because notice you got x squared minus 1 in the denominator. That means you can have a 0 in this denominator. So we need to find out what values of x that would give us a 0 in the denominator by setting that x squared minus 1 to be equal to 0. All right, in this case here, I have a difference of two perfect squares. So I'm going to factor this out as x plus 1 and x minus 1. One's a perfect square that can be broken up as 1 times 1. X squared is a perfect square. It can be broken up as x times x. One has to be plus, the other one has to be minus, for the difference of two perfect squares. So this is going to be equal to 0. And then we'll set each binomial factor equal to 0. So this means x plus 1 equals 0, or x minus 1 equals 0. And then for each term, each equation will solve for x. So for the x plus 1 equal to 0, this means x is equal to negative 1, or for the x minus 1 is equal to 0, x is equal to 1. So a negative 1 and a positive 1, I will get zeros in the denominator. All right, so let's see here. I'm going to draw a number line here. Is 0. It's not necessary. All right, now at negative 1 and at 1, I know I'm going to get a 0 in the denominator. Any x value less than negative 1 would work. Any x value between negative 1 and 1 would work, and any x value bigger than 1 would work. So its domain in interval notation is this, negative infinity up to negative 1, or from -1 to 1, or from 1 to infinity. Okay, so with the ones that have a quotient, you want to make sure you set your denominator to be equal to 0. And find out what values of x that will give you a 0 in the denominator. Okay. But for every polynomial function, its domain is going to be from -infinity to infinity. Okay. All right, next we'll look at the composition of functions, or composite functions. And it says here the composition of the functions f with g is denoted by this notation, f circle g. And it is defined by this equation. In this case here, f circle g of x, or the composition of f with g of x, is going to be equal to f of g of x, where the g of x is on the inside, the f of x will be on the outside. Okay. Now the domain of the composite function f circle g is going to be the set of all x, such that x is in the domain of g and your g of x is in the domain of f. Okay. All right, so in this case here, how will we do the composition of functions here? Here I got f circle g of x, which is the same as f of g of x. What that means is this: you're going to replace each x in f of x with that g of x function. You're going to start off with two functions, f of x and g of x. So for the composition of f with g of x, or f of g of x, the inside function is g of x. You're going to substitute each x in the f of x function with what g of x is equal to. And there's also g circle f of x, or g of f of x. This time, f of x is your inside function, where g of x is the outside function. In this case, you're going to replace each x and g of x with that f of x function. So let's look at a couple of examples of just this. Starting with this one. Let's say we got f of x is equal to 5x minus 2, and g of x is equal to 4x squared minus 4x plus 1. And in this case here, you want to find each of the following composite functions, starting with f circle g of x. All right, in this case here, I can write this as f of g of x, because that's what f circle g of x is, f of g of x. So now g of x is your inside function, and g of x is equal to the x squared minus 4x plus 1. So I'm going to bring down the f and replace g of x with what is equal to x squared minus 4x plus 1. So that means I'm going to be evaluating f of x squared minus 4x plus 1. Here, f of x is 5x squared. 5x minus 2. So I'm going to bring this down. Now here's where the substitution comes in. In the f of x function, I'm going to substitute each x with what g of x is equal to. So in this case here, here's f of x. This x is being replaced with what g of x is. This is your g of x, x squared minus 4x plus 1. So I'm going to substitute that in for x. And in the 5x minus 2, this x will be replaced with what g of x is. And here's what g of x is, equal to x squared minus 4x plus 1. So I'm just following this particular rule of replacing each x in f of x with what g of x is equal to. And that's what I'm doing here on the right side. And on the right side, I'm going to simplify this. I'm going to distribute the 5 by using the distributive property. 5 times x squared would be 5x squared. 5 times the minus 4x will be minus 20x, plus 5 times 1 will be 5. And bring down the plus 2 because that's part of the, I'm sorry, that should be minus 2. Because that's 5x minus 2. This should be minus, and this should be minus. Okay, from the minus 2 up here. Now let's combine some like terms here. 5x squared have nothing to combine with, and nothing to combine with the minus 20x, but 5 minus 2 would be plus 3. So the composition of f with g of x ends up being 5x squared minus 20x plus 3. All right, now part B is the composition of g with f of x. This time, the g is your outside function and the f of x is the inside function. So g circle f of x will be g of f of x. And here f of x is equal to the 5x minus 2. So I'm going to be evaluating g of, substitute f of x with 5x minus 2. Now here g of x in this case is the x squared minus 4x plus 1. So that means every x in this g of x function, I'm going to substitute it with what f of x is equal to. Notice you putting space around the parentheses here. And that exponent of 2 is part of the x squared in the g of x function. So now, in g of x, this x is replaced with what f of x is, which is 5x minus 2. So in x squared, I'm going to substitute the x with 5x minus 2. So I get 5x minus 2 quantity squared. And in the 4x, that x will be replaced with 5x minus 2. Now we're going to have to simplify the right-hand side of this composed function. That 5x minus 2, and it is squared. I'm going to write this off to the side as scratch work here. That 5x minus 2 is used as a factor twice. So I'm going to write 5x minus 2 twice because I'm going to be multiplying here. And then we're going to use the FOIL method. So that FOIL method is this. First times first. 5x times 5x. That's 25x squared. And then the outer would be 5x times a minus 2. That would be minus 10x. The inside minus 2 times 5x would be a minus 10x. And then the last times the last, minus 2 times a minus 2. That'd be plus 4. And if we combine like terms here, you're going to get 25x squared. Minus 10x and a minus 10x will be minus 20x, then plus 4. That's what 5x minus 2 quantity squared is. That's 25x squared minus 20x plus 4. Now for the minus 4 times 5x minus 2, we're going to use the distributive property. So in this case, you have to do minus 4 times 5x and a minus 4 times a minus 2. Minus 4 times 5x will be minus 20x. Then minus 4 times a minus 2 will be plus 8. And then I bring down the plus 1. And then next we combine like terms here. Let's see, bring down that 25x squared. Minus 20x and a minus 20x is a minus 40x. Then 4 plus 8, that's 12. 12 plus 1 would be plus 13. So the composition of G with f of x ends up being 25x squared minus 40x plus 13. Okay, now part C is on the next page. This time they want you to find the composition of f with G when x is equal to 2. That's what f circle G of 2 is. And another way of writing that would be something like this. F of G of 2. But if you look back at part A on that last page, we found the composition of f with G of x. So here, the composition of f with G of x, that ended up being 5x squared minus 20x plus 3. But here we want the composition of f with G when x is equal to 2. So let's use this right here, that 5x squared minus 20x plus 3, and substitute each x with 2. So here's what we're going to have. 5 times 2, and that's squared, minus 20 times 2, and then plus 3. And then we'll go and simplify this here. Let's see, 2 squared would be 4, so I'll go and write down the 5, and 2 squared would be 4, minus 20 times 2 would be 40, plus 3. Well, 5 times 4 is 20, and 20 minus 4 is negative 20. Negative 20 plus 3 will be negative 17. So at x equals 2, the composition of f with G of x would be negative 17. Okay. All right, let's look at another example of this. This one has f of x is equal to 5x plus 6, and g of x equals to 2x squared minus x minus 1. And we're going to find each of the following composite functions here. That is, the composition of f with g of x and the composition of g with f of x. And at the bottom is the composition of f with g of 0. Okay. So let's start with the composition of f with g of x, which is the same as saying f of g of x. So now your inside function is g of x, and g of x is that 2x squared minus x minus 1. So I'll just substitute that g of x with the 2x squared minus x minus 1. So I'm going to be evaluating f of 2x squared minus x minus 1. Well, f of x is 5x plus 6. F of x, that is the 5x plus 6 that's given to us here. So now, for every x in f of x, I'm going to substitute it with whatever g of x is. And in this case, f of x, this x is substituted with what g of x is, the 2x squared minus x minus 1. And then 5x plus 6, that x is substituted with the g of x, which is 2x squared minus x minus 1. So on the right side, I got 5 times the quantity 2x squared minus x minus 1 plus 6. So I'm going to simplify the right side by using the distributive property. If I do 5 times 2x squared, that's 10x squared, minus 5 times x, that's 5x, and then 5 times a minus 1 would be minus 5. Bring down the plus 6. And combine like terms here. Bring down 10x squared minus 5x, and then minus 5 plus 6 will be plus 1. So the composition of f with g of x will end up being 10x squared minus 5x plus 1. Okay, next we'll look at the composition of G with f of x as part B. All right, in this case, G circle f of x is the same as G of f of x. This time, f of x is your inside function and G of x is your outside function. The inside function is f of x, and f of x was 5x plus 6. So let's substitute f of x with 5x minus 6. And of course, my G of x is 2x squared minus x minus 1. And I'm evaluating G of 5x minus 6. So for each x in G of x, I'm going to substitute it with what f of x is. Okay? Then 2 times, I'm going to substitute the x, and then that's going to be squared minus the x plus 1. Minus 1. Okay. So in this case here, this x in G of x will be replaced with what f of x is. That's 5x minus 6. And in the 2x squared, that x will be replaced with the f of x, which is 5x minus 6. And then that's going to be squared, by the way. And in the minus x, notice that the parentheses in front of the minus sign, that's going to be replaced with 5x minus 6. And then have the minus 1 there. Now, take a look here. I need to bring this 2 down, because that 2 is going to be multiplied by the square of 5x minus 6. And just like I did in the last example here, I'm going to write 5x minus 6 twice, because 5x minus 6 is used as a factor 2 times. And then use the FOR method. So in this case, first times first, 5x times 5x, that's 25x squared. The outer 5x times a minus 6 will be a minus 30x. The inside minus 6 times 5x will be a minus 30x. And then minus 5 times a minus 6 times a minus 6 will be a plus 36. Okay. Now, if we combine like terms here, we got 25x squared minus 30 times minus 30 will be a minus 68x, just minus 60x, and then plus 36. So 5x minus 6 quantity squared will be 25x squared minus 60x plus 36. Now this has to be multiplied by 2, the 2 in front. And then we're going to distribute the negative over the 5x minus 6. So that negative will make 5x minus 5x. The negative will make, the minus sign will make the minus 6 a plus 6. I still got that minus 1 out there, so I'll bring that down. All right, next. Distribute the 2 over the 25x squared minus 60x plus 36. I'm going to get this. 2 times 25x squared would be 50x squared. Minus 2 times 60x would be 120x, plus 2 times 36 would be 72. And then minus 5x plus 6 minus 1. Now, combine all these like terms here. Here we got 50x squared, bring that down. Minus 120x minus 5x will be a minus 120. I made a mistake here. This should be a +6. Or did I make a big mistake here? This should be a +6. There's a problem that says 5x, f of x is 5x plus 6. Okay. And that's going to change the middle term to a plus. So this would be plus 30x and a plus 30x will make that a plus 60x. Okay. And that's going to make minus 120x a plus here. Okay. I just made a mistake here. It was 5x plus 6, not 5x minus 6. Okay. So negative 100, plus 128x minus 5x would be a plus 115x. And let's see, 6 minus 1 is 5. Correction. There's another correction I need to make. This minus will make the plus 6 minus 6 when I distribute the minus sign. So that's going to be a minus 6 here and a minus 6 here. Okay. 72 minus 6 would be 66 minus 1 would be a plus 65. Okay. Hopefully you understand where I messed up at, because I wrote 5x minus 6 where it should be 5x plus 6, which is what f of x is on your handout. Okay. So here, the minus sign makes a 5x minus 5x, and the minus sign makes a plus 6, a minus 6. Okay. So this is what happens when you miscopy a problem. You end up getting the wrong answer. Okay. All right. Part C, we got f circle g of 0, which means f of g of 0. So I'm going to find the value of that composed function when g of x, when x is equal to 0. But I already know what f circle g of x is from part A. And that's this, the 10x squared minus 5x plus 1. Okay. And here, I want to find the composition of f with g when x is equal to 0. So all we do there is just substitute 0 into that composed function. So it'd be 10 times 0 squared minus 5 times 0 plus 1. Well, this is going to be easy. 0 squared is 0 times the 10 is 0. Minus 5 times 0 is 0. And you'll end up with 1. So the composition of f with g of x when x is equal to 0 is just going to be 1. Okay. All right, so that's how we do the composition of f with g and the composition of g with f. Okay, and especially on part B, if you have questions, do email me if you have questions about that. Okay, the last thing we'll look at is decomposing functions. You will have a function that's already composed. You want to break it apart by finding out what f of x is and what g of x is. All right, in this case here, we're letting h of x is equal to the composition of f with g of x to be this, f of g of x, where the g of x is going to be the inside function, f of x will be the outside function. Now, there are 4 possibilities for this. One of them could be this. If you have h of x equal to some algebraic expression raised to a power, the inside function is going to be g of x. So that means your algebraic expression on the inside will be g of x. And f of x would be x to some power because of the fact that g of x was substituted for x in f of x to get this. So f of x will be x to some power, g of x will be some algebraic expression. And then next, another possibility would be this: h of x is equal to the square root of that algebraic expression. Well, what's underneath the radical would be your algebraic expression. And I shouldn't say square root. This should be the nth root, because it could be the cube root or the fourth root or the fifth root or whatever. G of x, what's underneath the radical, will be your algebraic expression, meaning that this algebraic expression was put in place of x in f of x. So f of x started off as n times the nth root of x, just the nth root of x. That would be what f of x is. And then the third possibility would be where you have the absolute value of the algebraic expression equaling to h of x. So what's inside those absolute value bars would be your algebraic expression. And f of x would be the absolute value of x, because this x was replaced with that algebraic expression. Okay. And h of x equals to 1 over the algebraic expression. This is the fourth possibility. Well, in this case here, what is in that denominator will be your g of x, the algebraic expression. So that algebraic expression was put in place of x, so that means f of x will have to be 1 over x. All right, so now let's look at some examples of how to express as a composition of two functions. Here we got h of x is equal to 2x minus 5, and that quantity is to the third power, or cubed. And I want to find out what f of x is and what g of x is. All right, in this case, let's take a look. The inside function, what's on the inside of the parentheses, is your 2x minus 5. That's going to be your inside function, which is in this case g of x, because g of x is always going to be the inside function. F of x is always the outside function. So your g of x is going to be that 2x minus 5. And this was put in place of x in the f of x. So f of x had to have the x in it, and it's going to be raised to the third power. So f of x is equal to x cubed, and g of x is equal to 2x minus 5. Okay. All right, the rest of these on the next page. Here's part B. H of x is equal to the square root of x squared plus 5. So here I want to find out what f of x was and what g of x was. All right, in this case, what's underneath the radical will be your g of x. That's your inside function. So here, that x squared plus 5, that's your g of x. What's underneath the radical will be your g of x. So in this case, your g of x will be x squared plus 5. And that x squared was plus 5 was substituted, was put in place of x in f of x. So f of x had to start off as the square root of x. Okay, now part C is h of x equaling to the absolute value of 8x plus 6. So again, I want f of x and g of x. Well, what's inside that absolute value symbol? That's that 8x plus 6. That has to be the inside function for g of x. So 8x plus 6 is what g of x is. And since the 8x plus 6 was put in place of x in the f of x function, f of x had to start off as the absolute value of x. And then finally, part D, h of x is equal to h of x equals to 1 over 4x plus 5. And here I want f of x and g of x. Well, my denominator is that inside function g of x. So that's your 4x plus 5. Okay. So this has to be g of x. And since that g of x was substituted for x in f of x, the f of x function had to start off as 1 over x. Okay, so that's how we decompose functions here. In this case, write it as f of x and g of x, because h of x is the composed function f of g of x, where g of x is the inside function. Okay, so that will conclude this video on section 2.6, which deals with combinations of functions and composite functions. Please feel free to email me if you have any questions about any of the examples that were done on this video, or if you have any questions about the homework in my math lab.